Batasang Una ang pagmamalasakit.
Today, the DOH is reporting 2 additional confirmed cases of
Nitong mga nakaraang buwan, humarap ang bansa at ang buong mundo sa isang pandemya. Nangangailangan ng mga bagong bayaning matapang nahaharap at tutugon sa mga pangangailangan ng komunidad. Isa ang Polytechnicong Universidad ng Pilipinas na tumugon sa panawagan sa pag-aali ng malasakit sa kapwa.
Ang PUP ay tumutugon sa pangangailangan ng ating mga mahihirap na kabarangay.
Sa pangunguna ni PUP President Dr. Manuel M. Muhi, mga kaguruan, empleyado, alumni, at mga estudyante ay nagpahatid ang universidad ng pagmamalasakit sa iba't ibang paraan. Libo-libong mga frontliners ng ospital, nakadestino sa mga karatig barangay, at police stations, at mga tricycle at pedicab drivers ang nabigyan ng alcohol na locally produced ng Institute for Science and Technology Research.
Alcohol na ipinamamahagi namin sa mga tao dito kasi kailangan natin ng alcohol. Yun ay kaloob din ng ating universidad sa nasasakupan ng barangay. Kaya ako, in behalf of my council, kami ay nagpapasalamat ng marami sa ating universidad dahil hindi tayo pinababayaan sa lahat ng, lalo itong pagkakataon na to, na talagang lahat naman na kailangan ng tulong. Nakita ko naman sa ating universidad ang magaling at mahusay na pagsuporta sa ating pamayanan.
Sa panahon na hirap ang ating mga kababayang makatanggap ng tulong medikal, ay nabigyan ng psychological at medical assistance ang ilan sa mga miyembro ng universidad na nakaranas ng iba't ibang karamdaman noong nagsimula ang pagtaas ng kaso ng nasabing sakit sa bansa. Sama-sama ring binuo ng Medical Services Department at Facilities Management Office ang isang triage sa loob ng PUP Santa Mesa Campus para masigurado ang kaligtasan ng mga empleyado na papasok sa universidad. Bilang dagdag na proteksyon laban sa COVID-19 ay nag-produce din ang PUP ng face shields. Ito ay ipinamahagi sa iba't ibang ospital, opisina ng gobyerno, kalapit na barangay, Philippine Red Cross, at miyembro ng komunidad ng PUP. Hindi rin lingid sa kaalaman ng lahat na nang maipatupad ang Enhanced Community Quarantine o ECQ ay may mga estudyanteng na stranded sa kani-kanilang dorm at hindi makauwi sa kani-kaniyang probinsya. Linggo-linggong ayuda mula sa iba't ibang benepisyaryo, maging sa bulsa ng mga empleyado at faculty members ang naipamigay sa mga nasabing estudyante.
Una po sa lahat, nagpapasalamat po kami sa PUP kasi malaking tulong po yung nabibigay nila sa amin na bilang kami po ay hindi po nakakauwi. Natutulungan po nila kami sa aming pagkain sa araw-araw. Every week po silang nagbibigay sa amin ng ayuda po, lalo na po yung mga tao sa admin po.
When the pandemic started, I didn't have food as well. But when I knew that PUP will distribute food for stranded students from PUP, I was extremely excited and I felt really lucky.
Sa tulong din ng Armed Forces of the Philippines at iba pang ahensya ng gobyerno, ay may naiuwi ring mga estudyante sa kani-kanilang pamilya.
Fortunately, OAA, they did their best to have us finish every document to renew our student visa. After a few weeks, we finished the document of my student's visa. I received a news from Vietnam that they will send a repatriation flight from the Philippines to rescue Vietnamese people here.
Sa darating na pasukan ay haharap ang buong universidad sa new normal. Sasalubungin ng mga estudyante, administrador at kaguruan ang tinatawag na FlexTel o Flexible Technology Enhanced Learning. Sinisigurado ng FlexTel na walang estudyante ang mapag-iiwanan sa pagbibigay ng kalidad na edukasyon. Sa FlexTel ay hindi lamang iisang forma ng delivery ang gagamitin ng mga kaguruan para masiguradong lahat ng estudyante kabilang sa iba't ibang antas ng lipunan ay makapag-aaral. Ilan dito ay ang face-to-face learning sa panahon na maaari nang magbukas ang mga eskwelahan, nasisiguraduhin ang kaligtasan ng mga estudyante at guro sa pamamagitan ng physical distancing, iba't ibang health and hygiene measures, bawas na bilang ng araw na pagpasok, at mas maliit na bilang ng estudyante sa classroom. Online na maaaring synchronous o asynchronous learning na re-respeto sa ekonomikal na kakayahan ng estudyante. At digital at off-grid na magpapadala ng instructional material sa mga estudyanteng walang gadget o walang kakayahang kumunek sa internet dahil sa ekonomikal na estado ng kanilang pamilya o lugar. Dinedevelop na rin ng mga kaguruan ang instructional materials para sa iba't ibang klase na tutugon sa pangangailangan ng mga estudyante sa new normal. Kabilang sa paghahanda ay ang pagmimintina ng mga classrooms, paglilinis ng mga pasilidad, at pag-conduct ng mga regular na meetings para sa development ng iba't ibang sektor. Sa kabila ng takot at pangamba, hindi tumitigil ang mga iskolar ng bayan para tulungan ang isa't isa. Tunay ngang kahit sa panahon ng panganib ay isinasapuso ng bawat PUPian ang mga salita sa himno. Gagamitin ang karunungan mula sa iyo para sa bayan.
Okay. Good morning, everyone. Welcome to Polytechnic University of the Philippines Professorial Chairholder Lecture Series. Today, we will have two experts that will be giving their lecture this morning with Dr. Della and later in the afternoon with Dr. Evangelista. I am your host or master of ceremony for today. I am Engineer Orland D. Tobola. This program is organized by the College of Science, College of Engineering, and Institute of Technology. To start, let us feel the presence of our Lord through the singing of doxology and renew our vow and devotion to be a productive citizen of our country through the singing of the Philippine national anthem.
Noon pa man, malaki na ang naging bahagi ng mga kababaihan sa lipunang Pilipino. Kaisa sila sa marubdob na paghahangad ng kalayaan ng ating lahi. Kabilang sila sa paglinang ng ating makulay na sining at mayamang kultura. Kasapi sila sa pagtataguyod ng mga adhikain ng kapwa mamamayan at sa pagtugon sa mga pangangailangan ng lipunan. Katuwang sila sa pagtuklas sa mga larangan ng agham at medisina. Kapanalig sila sa pagpapairal ng batas, karapatan at katarungan para sa lahat. Kabahagi sila sa paglilingkod sa bayan at sa pagpapanatili ng demokrasyang Pilipino. Sa paglipas ng panahon, hindi nagmaliw ang kanilang pag-ibig sa ating inang bayan. Mga kababayan, ito ang alay ng mga kababaihang Pilipino para sa bayan. Tumayo po tayo.
Bakit yun stop? Sorry.
Yung lahat at sabay-sabay nating awitin ang pambansang awit ng Pilipinas.
Ayaw mag-iiw, pero sa silanganan, ayaw ng puso, sa tingin mo'y buhay. Lupang hinirang, gulot ka ng mag-iiw, sa manlulupang, ikaw masisingin, sa lahat ng pagkakasingin, at nangyari mo mga, may ginagang tulad ang ngayon ay lamang, ang isang ng watawat, ay nabuhay na nangyayin. Tuwing nag-araw ng kailan ang bayani, lumang araw na lamuan aking pagsigaw, buhay ay langit sa piling mo. Ang hikaya ng pagkay magkakamit, ang mamatay ng dahil sa'yo.
Okay, to smoothen the flow of our virtual conference, we would like to request our participants to adhere to the following virtual conference etiquette. Kindly change your Zoom meeting ID to this format, acronym of the institution you are affiliated with, and full name. Example, PUP Juan de la Cruz. Otherwise, you may use your full name as meeting ID. Remember that your microphone and video camera are disabled by default. You may enable them if it's your turn to interact. Be respectful, don't interrupt the presenter, and keep your mic on mute and camera off while someone is presenting to avoid unnecessary distractions. Be an active participant. Provide inputs and respond to the speaker's request for comments or questions. Next, questions and clarifications will be entertained after the presentation. You may use the chat box for the facilitators to note them. State your name and institution and ask questions concisely. Comments that will benefit others are most welcome. Also, provide feedback. Help us improve our online events to better understand your needs and preferences. For our registered participants who are on Facebook, make sure that you have answered the survey feedback to ensure that you will receive an e-certificate. Whenever disconnected in the Zoom meeting, please log in again using link, or you may join us at facebook.com/PUP Alumni Official. So, to formally open our program today, let us welcome the Executive Director of PUP Open University System, Dr. Carmencita L. Castolo, for the welcoming remarks. Ma'am?
Thank you very much, Engineer Tubola, and good morning to everyone. Magandang umaga po sa ating lahat. To our
Magandang umaga po.
university president, Dr. Manuel Muhi, to the Dean of the College of Engineering, Dr. Remedios Ado, to Dean and Honorable Regent, Engineer Ramir Cruz of the Institute of Technology, and the Dean of the College of Science, Dr. Lincoln Bautista, PUP officials and faculty members, and of course, our participants and guests from other universities and colleges. On behalf of the Vice President for Academic Affairs, Dr. Emmanuel de Guzman, I warmly welcome all of you to this very important event of the Office of the Vice President for Academic Affairs and the Office of the Research Extension and Development. Welcome to the PUP Professorial Chairholder Lecture Series in the areas of science, engineering, and technology. Today's activity of the two sectors is a regular gathering of the administrators and faculty members, although this time it is virtual. The Professorial Chairholder Lecture Series of PUP present experts and notable speakers in various academic disciplines to share their knowledge, expertise, and innovative ideas. The professorial chairholders are recognized of their academic excellence and meritorious service in the field of teaching and in research, and who has sustained dynamic scholarly involvement in teaching, research, community service, and the industry in accordance with the mission of the university. We are so fortunate that our guests this morning are known speakers in the field of engineering, science, and technology. Thank you very much, Dr. Della and Dr. Evangelista, for giving us this opportunity to hear from your lectures on the topics. Likewise, I thank the organizers of this event, especially the College of Engineering, the College of Science, and the Institute of Technology. Our sincerest gratitude also to our Vice President for Academic Affairs, Dr. De Guzman, our Vice President for Research Extension and Development, Dr. Ana Rubiga Pasin, and of course, our University President, Dr. Manuel Mohi, for the approval of this activity. Again, I wish a warm welcome to all, especially to our participants. Let us enjoy and at the same time learn from this lecture series. Muli, maraming salamat po at magandang umaga sa ating lahat.
Thank you, Dr. Castolo. To introduce our professorial chairholder for today, let us welcome the co-chair of the Professorial Chairholder Lecture Series Committee, Engineer Joselinda Golpeo.
Good morning. Our guest speaker for today is a graduate of Bachelor of Science in Mechanical Engineering at St. Louis University in Baguio. He finished his Master of Science in Mechanical Engineering, major in Machine Design, in 2001 at the University of the Philippines, Diliman. While he has his University of Glasgow, Singapore Leadership Development Program in 2015 at the University of Glasgow, Singapore. He has also an executive certificate in leadership and people management from the Singapore Management University in 2017, while he has his postgraduate certificate in academic practice in 2019 at the University of Glasgow in UK. He finished his Doctor of Philosophy in Engineering Mechanics in 2006 at the School of Mechanical and Aerospace Engineering at the Nanyang Technological University in Singapore. He received several certificates and relevant trainings. He is a fellow of the Higher Education Academy at the United Kingdom. He also has a certificate in university teaching at the University of Newcastle, Australia. He has a Six Sigma Green Belt at Vestas Technology R&D Singapore, and he also has a Design for Quality and Reliability training at Vestas Technology Research and Development in Singapore as well. His research interests include applied computational mechanics for mechanical design, composite materials and structures. He's also an expert at piezoelectric composites for biomedical engineering applications, and of course, in engineering education. His courses being taught includes engineering mechanics, mechanics of materials and structures, mechanics of solids and structures, structural analysis, finite element analysis or FEA, computational fluid dynamics or CFD, mathematical modeling and simulation, machine design, and advanced machine design. His professional experience include being the assistant professor up to present at the University of Glasgow, Singapore, a professional lecturer from the Department of Mechanical Engineering at the University of Diliman, Philippines. He's a consultant at Principia Engineering and Technology Center, Philippines. He is also an assistant professor at the University of Glasgow, Singapore from 2012 to 2017. And for a final year project supervisor from 2015 to 2017 at the University of Newcastle, Singapore. He is also a seasonal or sessional lecturer at the University of Newcastle, Singapore, an associate principal for research and development engineer, and a lead engineer from 2008 to 2012 at the Vestas Technology Research and Development, Singapore. He is a visiting research fellow from 2008 at the School of Engineering Sciences at the University of Southampton, UK. He is a research fellow as well at the School of Mechanical and Aerospace Engineering at the Nanyang Technological University, Singapore. And he is a teaching assistant at the School of Mechanical and Aerospace Engineering. He also have several academic lectures and trainings conducted on simulation-driven engineering, as well as international publications in different journals. He also have several conference papers and oral presentations, being a seasoned researcher. So for the postgraduate supervision and postgraduate external examiner, both for different universities in UK as well as in Singapore. So for the reviewer of international journals, his portfolio includes that of composite structures, thin-walled structures, journal or applied physics, composites part A journal of aerospace engineering, in a Journal of Sound and Vibration and other journals as well. He is a member of the Higher Education Academy of the United Kingdom Fellow, an American Society for Engineering Education or ASEE member. He is also a member of the Institute of Engineers Singapore or IES and a Philippine Society of Mechanical Engineers or PSME, Mechanical Design and Fabrication Technical Division Chair. Ladies and gentlemen, our guest for today, Dr. Christian and Della.
Good morning po sa lahat. Thank you very much for the introduction po. Salamat po. Welcome to everybody. Welcome to this lecture on piezoelectric composites. I'd like to first thank the Polytechnic University of the Philippines for giving me this opportunity to share my knowledge in composites, as well as share also the results of the research that I have done in the area of piezoelectric composites. So I'd like to share my slides. So welcome to this lecture on piezoelectric composites. I'm Christian Della. I'm currently an assistant professor at the School of Engineering, University of Glasgow, UK. I'm currently based in our Mechanical Engineering and Aerospace program in Singapore. As an outline of my presentation, I'd like first to introduce composite materials. This is where I started my journey of research here in Singapore. So even though this is a very old topic, I still believe that this one is still an active research because of the new materials coming out, as well as the new and advanced manufacturing processes that's being currently introduced. I then proceed with giving an introduction on what piezoelectric material is, which is basically a smart material. And finally, I'm going to discuss piezoelectric composites, as well as share some of my publications or results of my research in piezoelectric composites. So like I said, composite materials is not really new. Marami po siyang application, especially sa aerospace, being because this one is lightweight and strong. Of course, we have boats and the ships being using these composite materials. Of course, cars are also using them. We have the wind turbine blades. I've spent about 4 years of working on the wind turbine blades for the Danish company Vestas, and still I think Vestas is still the #1 wind turbine manufacturing company in the world. Now, having said that, we cannot just limit ourselves to synthetic composite materials. There are also many natural fiber composites or natural fiber reinforced composites out there that we can utilize, especially in the Philippines. We have a rich resource, or we have many resources on this natural fibers. So what is composite material? So basically this one is defined as 2 or more materials with very different properties. They are combined together to form a different material. Now, what's the difference between a composite material and an alloy? So in an alloy, there's this so-called mixing, while when it comes to composite materials, the 2 materials when mixed are basically distinct. They are present, while for an alloy, you cannot see the difference between the 2 materials already because they are mixed. Unless, of course, you look at it from a microscopic point of view. But for composite materials, you will be able to see that the 2 materials that we put in together are basically distinct. So each of these materials are going to form a synergy. They're going to support each other. The early composites that has been recorded, of course, was back in 3000 BC, where we have this bricks with straws. So they have been doing this one already. So the straws has been providing some support so that you can actually connect those clays. Okay? It also prevents cracks from occurring within the clay brick. So basically, this has been used before. And for composites now, as you can see, we have this aerospace applications, or so for example, in Airbus, so we see a lot of parts there that have been using composites for different areas. Of course, they have to be designed so that they're going to be their applications will be specific to how they're going to be used. For aerospace, they're more focused on carbon fiber composites or carbon fiber reinforced composites, because these carbon fibers are basically strong and they are lightweight. Of course, why does this aerospace engineering prefer to use this lightweight and strong? Of course, they have higher payload. Of course, the investment will be very high initially, but in the end, they will be able to get those investments. So basically, the reason why we have this composites is because they are strong and lightweight. So I'm talking about the synthetic carbons like carbon fiber composites, as well as glass fiber composites. The other advantage on the use of composites is because they can be tailored to specific applications. You don't really need extra machining processes to be able to form these composites. So basically, you need some molds. You need to just do some simple processes to be able to form that composites, and that can be applied to the applications that you would like to. So as you can see, they have been many of the parts of the new cars or the advanced cars are using composites nowadays. So the only problem with this one is that it can be very expensive, and of course, there's also that issue of repair when it comes to composites. Now, these are typical examples of composites that we see. So we see concrete, of course, it's a mixture of cement and aggregate. So you can see them. I mean, there's no mixing there, but you will see them to be distinct after the mixing process. So each of these materials are going to support each other. So basically, concrete is considered to be a composite material, not an alloy, of course. We have the fiberglass. So probably a lot of us or somebody here who has worked in the oil and gas industry would see a lot of this composite pipes. They are made of fiberglass. And the boats that we are using, some of the advanced boats that are being used, the hull is basically made of fiberglass. And then we have carbon fiber. So the light bodies of the bicycles basically are made from carbon fiber. They are strong, they are lightweight, but of course, they are expensive. So for advanced composites, they are extensively used in a wide range of engineering products, such as transportation. You have aircrafts, boats, warship. Of course, we have the marine structures and sports. So as you can see, the reason why they use this one in sports, of course, if you want to win the competition, then you want to use something that's high performing and of course, light and strong. But of course, it comes with a price. It's expensive. What about natural composites? Do we have them? Yes, of course. We have wood. Basically, there's quite a number of materials in that wood. Basically, we call it wood, just one material, but basically inside the wood, you have basically some so-called fibers, and you have a so-called matrix, the glue that binds the fibers together. And we have the bone. So basically, a bone is a composite. So it consists of different materials. They are arranged in different ways. They have their own functions. And as you can see, it's very complicated to model this bone. I mean, we can say that they are very common out there, of course, bones. But the thing is that inside the bone, there are so many materials, and modeling a bone is not really simple. So this one is an introduction, further introduction of the composites. By the way, my PhD, when I started my PhD back then, that was way back in 2002, if I remember correctly, yes, 2002. So I did my work on composites. Still during that time, it's not really something new, but it was still a good research area. And even now, even though we say that composite materials is very common, I still believe that it's still an active area, especially in the Philippines, where we have a lot of natural fibers that we can use for our composites. And this is why I would like to provide first an introduction on composites before I go to the piezoelectric composites. So the composition of the composites, we have a matrix, a binder, or a glue that surrounds the reinforcement. So basically, the purpose of the matrix material is basically to glue those reinforcement together. So that's the purpose of the matrix. So we have a matrix and a reinforcement. So the reinforcement can be in the form of a fiber, can be in the form of flakes. So they can be distributed, or they can be so-called continuous fibers, or even cut fibers. So these are the types of composites. So we have laminar composites. So basically just putting two homogeneous material on top of each other, you basically have a composite. Basically, based on the definition, you have two materials being joined together. After joining them together, the two materials are still distinct, but they both contribute to improving the performance of the composite material. So we can also have fiber reinforced composites, as well as a particulate composite. So as you can see, this fibers here and these particulates here, they can be called reinforcements, while the glue that binds them together is called the matrix. So to your right side, we have an example of the laminate. So we can put this fibers and glue together on top of each other to be able to form a laminate. We also have a sandwich structure, or sandwich composites, where we have a light material in between these two stiff and light facing, or what we call the laminate, or the so-called sandwich cover. All right, so this is basically some of the common composite materials that we can see out there. Actually, the aerospace is using the honeycomb sandwich. They are stiff, they are light, and they are good enough for their applications. So what are the types of composites? So they can be classified based on the matrix that they are using. Some are using ceramics as a matrix, so they are a ceramic matrix composites. We also have polymer matrix composites, polymer or plastic. So this polymer can be of two types. We have the thermoplastic, where you can melt and remelt them every time you want to use them. And the thermoset, that once you have melted them, once it sets, then it's already fixed. And then we have the metal matrix composites. So we have the metal as the reinforcement, and then, we have other reinforcement, and the metal here will be serving as a glue. to bind those reinforcement. Or it can be just also a metal composites, wherein metal is a matrix, while the reinforcement will also be made of metal. And then we have different types of composites based on reinforcement. We have fiber reinforced composites. We have particulate composites, and we have the structural composites. So this structural composites includes the sandwich and the laminated composites. Now, what will be the choice of our fibers? We have the strength and stiffness, thermal expansion, electrical and thermal conductivity, and cost. Well, in the wind turbine industry, well, I'm going to share wind turbine industry because I've worked there for almost 4 years. So my area was really in the blades of the wind turbine. We are using glass fiber composites. Why? Because it's cheap. Why not carbon? Why not carbon? Why do we use glass fiber composites? It's light, heavier than carbon fiber, but the thing there is it's a lot cheaper than the carbon fiber composites. But there are also some areas in a wind turbine blade that uses carbon fiber to make it more stronger and make it more lighter. So as you can see, the wind turbine blades now can be the largest that they were able to develop now is about 100-meter blade. Then when I started, the larger wind turbine blades, or the largest wind turbine blades, was about 50 meters. And I was part of the team that conducted research in supporting the development of the 90-meter blade. So that was the until recently, that was the largest or longest wind turbine blade, which was broken by GE. So the GE wind turbine blade is now 100-meter long. So these are the reasons why we choose the different types of fibers for our reinforcement. Of course, when it comes to the aerospace industry, they would prefer to use carbon fiber, strong and light. Of course, for them, cost probably may not be an issue, or it can be one of the issues, but of course, they would like to have more payload. And of course, their safety requirements are very high. So they have to use something that's quite proven, that's light and strong. For the new cars that's coming out, or for the expensive cars, luxury cars, they use carbon fiber composites. They are light and they are strong. But then again, the problem there is the repair as well as the cost. So here are the different types of carbon fiber reinforced polymers. So we have the automotive parts in the car. So those that are going to be used for structures or structural application. We have the aerospace and aircraft industry. We have the sports equipment. So these new bicycles coming out, the expensive ones, basically they're made of carbon fibers. We have energy production. So like I've mentioned with the wind turbine blade, we use both the glass fiber and the carbon fiber. So if we want to really make it strong and light, then we use more carbon fiber, but basically most of its components are made of glass fiber composites, but we also use sandwich in here. So there's quite a lot of materials going on inside the wind turbine blade. It probably looks simple because once it's painted, you cannot see what's inside the wind turbine blade. But inside it, there's a lot of materials. There's a lot of design considerations, and of course we have the civil engineering. There are quite a number of research when it comes to using composite materials for bridges. So what about natural fibers? Let's see. So we have here rice husk, we have banana, we have cotton, we have coir. So basically we're rich with coconut coir. I think the Philippines is like the second or the third coconut producing country in the world. Abaca, we're the #1, of course. What else do we have? So I think we have bamboo, so it's not here. Of course, we have lots of rice husk that we can use. So instead of burning this one, we probably can repurpose the rice husk to become composites. And there is this now the work or the product by Mercedes-Benz on this C-class of automobiles. They are basically using about 30 parts of the Mercedes-Benz are made of natural fiber reinforced composites. Of course, we have to be practical here. The natural fibers are not too strong as compared with the other synthetic fibers. So the parts that are being used here are basically for non-structural application. They're just secondary structures. So there's a lot of debates. Why do you use this natural fiber composite? It's not too strong. Yeah, but I mean, you're not going to use them. You're not going to use them for structural applications. They're basically for secondary applications. So I think that the reason here is basically more for sustainability. So if we make these parts out of the synthetic materials, then we're basically trying to pollute the earth. And I think companies should now be more responsible in developing their products. They should also look in sustainability as well as waste. There are also a lot of applications of this natural fiber reinforced composites, from packaging to some aesthetic designs or aesthetic structures. So here you have sugarcane-based panels. You probably have the roof made of bamboo, but if you're going to use some natural fiber composites and you're going to apply them or use them for external purposes, you probably would like to use some synthetic matrix, meaning synthetic material that's going to glue this bamboo together. Now, there are, well, according to this review in recently 2020, there basically are some commercial applications of the green composites. There can be in the energy sector, the automobile. Of course, we have seen examples already of some many luxury cars. We can use them for packaging as well as medical applications. And of course, it doesn't limit us to explore the use of natural fiber composites in building construction. So I know a lot of this has been done already, and this is just a literature review. I've actually seen the work of the Philippine Coconut Authority on the use of the coconut fiber composites to build the home. So it's not something new, but probably it's something that we can further explore as a research topic, and hopefully we can improve its performance and be able to make it more common. To me, I believe that there's a lot of applications here for the natural fiber composites. At the moment, may not be for structural applications, but in terms of secondary structures, there's quite a lot of applications there. In terms of research, because we're academic, there's still a way to publish in this area. Definitely, I believe that this is still an area where a lot of us can still publish in international journals. So I'm pretty much, I'm very picky about choosing the journals where I have to publish. And I have seen a lot of these natural composites being published in high impact factor journals. So what about metal matrix composites? So you're looking at a metal that is, a composite that will be having its matrix as metal. So for example, aluminum and silicon carbide. Silicon carbide is ceramic. That will be its reinforcement. And then you have the matrix, the glue that binds together this reinforcement will be the aluminum. So silicon carbide, it's ceramic, it's strong. It has very high thermal resistance. The only problem with ceramic is that it's brittle. So basically, brittle means that it doesn't have any warning before it fails. So we add that with aluminum, which is typically a ductile material. So we have a nice combination, one supporting each other. So aluminum is weaker than silicon carbide, but it's ductile, while silicon carbide is strong, have a high thermal resistance, but it's brittle. So we have this combination. So it's basically a synergy between the metal and the ceramic material. So these materials can be used so these composites use a metal such as aluminum as the matrix and reinforced with fibers such as silicon carbide. They can be increasingly found in the automotive industry. And then we have ceramic matrix composites, meaning that the glue that binds together is ceramic, and then we can have other reinforcements. So reinforcements can also be in the form of ceramics. It can be in the form of, metal as well. So basically, you can combine a lot of these things, and I hope that there's a lot of applications. And then we have the more common polymer matrix composites, polymer meaning plastic. So you can see them because there's already a mature technology in using plastics. So they use the polymers to bind the reinforcements together. So different types of fibers can be the carbon fiber composites. We have the aramid fibers, they are used for defense. And then we have the more common glass fiber composites. And back in 2001, there was the study on the use of composites to be able to address the biomaterials. So as you can see here, the bones itself, the replacements of the knee replacements, the teeth. So basically they can be made of composites. So even the human body. So basically we are basically made of composite materials as well. And I'm going to link this one later on with the piezoelectric composites. Now, after the discussion on composites, I'm going to discuss smart materials. So basically smart materials, they are called the intelligent materials. So they have one or more properties that can be significantly changed in a controlled fashion by external stimuli. So this external stimuli can be in the form of stress, moisture, electric, or magnetic field. So basically what we're saying here is that we have a material, we apply a stimuli, it can be a heat, it can be a force, and then we see some changes. We see this one to be giving out electricity, or if we put in electricity, it's going to give out a displacement. So basically these are smart materials. Now again, we humans, we're made of a lot of smart materials. So even if we're not thinking, sometimes we do actions because of the external stimuli. And these are what we call basically the smart materials. So they can act as sensors, or they can act as actuators, or they can be both sensors and actuators. So this now brings me to piezoelectric material, which is basically a smart material. So piezoelectric material, they can be made of different materials, barium titanate, PVDF, and then lead zirconate titanate, or the more common PZT. We see these piezoelectric materials to be used in a lot of applications. Probably many of us won't know it. Ultrasound basically uses piezoelectric materials. So piezoelectric materials is a smart material, and what's good about piezoelectric material is it can act both as a sensor and an actuator. So what is piezoelectric materials? Piezo meaning force, and electric, of course we know electric, meaning that if we apply a force to a piezoelectric material, it's going to give out electricity. If we're going to input electricity to the piezoelectric material, we're going to get a displacement. So that is piezoelectric material. So piezo meaning force, and electric meaning force electric. You input a force, you get an electricity or voltage. You input a voltage, then you get a displacement. So that makes this piezoelectric material very applicable as a sensor and an actuator. So we have this inverse effect. So I was telling you earlier that once you apply a force to this piezoelectric material, then you will be able to have a voltage. So that is the direct piezoelectric effect. So the inverse piezoelectric effect is trying to put in a voltage, applied voltage, and then there will be a displacement. So that is the inverse piezoelectric effect. And it's not new. This has been discovered in 1880 by the husband and wife, Jacques and Pierre Curie. And like I mentioned earlier, so this one, piezoelectricity is defined as a change in electric polarization with a change in applied stress. Piezo, force, electricity. So that's electric. So you have force and electricity. And we have the converse effect, change of strain in the material due to the applied electric field. There are many applications. They can be used as piezoelectric motors or ultrasound generating devices, such as what we use for ultrasound, the medical products, ultrasound. Basically, they use piezoelectric materials. So other applications include sonar. So basically those ultrasonic transducers, they normally would use piezoelectric materials. In engineering, we have the non-destructive testing. They can be used for pressure measurements to study explosives, vibration and accelerations or impact. And they can be used as microbalances for chemical and biomedical or biological sensors. So there's a lot of applications from aerospace to precision manufacturing to MEMS or microelectrical systems, and we have the flexible robots. Do take note that yes, the robots are becoming common, so it's making them more smart to be able to react to different stimuli. And these are the typical energy harvesting operations for a piezoelectric material. So the reason that we can use this one for harvesting energy is because of the nature of the piezoelectric materials itself. So do take note that we apply a force to a piezoelectric material, we can output electricity. So in this case, the displacement here can be coming from the action. So maybe in a bridge, you install them, and then there will be a displacement there because of the loading conditions, and then you can generate some electricity. So even human motion, there are studies there, vehicle vibration, and so on. So what I'm going to do is pretty much just share you a typical undergraduate work project by my student showing that we can really harvest some energy in a piezoelectric material using the concept of a cantilever beam. So this one is a simple work that my student did. At the end of this this cantilever beam, you will see piezoelectric there, and you will see that we are, because of the vibration, we are able to harvest some energy. We want to use this one in a location where there's high traffic, maybe bridges or probably some applications where there is a bit of vibration to be able to harvest that. We were able to see that it's small. Yes, it's possible, has been proven to be possible. But the thing is that we really cannot harvest much energy there. So still, I believe that there's still a lot of research there ongoing to be able to harvest this energy coming from the piezoelectric or coming from the normal actions that we do. And with that, this now brings me to the research topic of mine, the piezoelectric composites for biomedical applications. So we have, I've mentioned about a matrix, and I mentioned about a fiber. So the fiber here is going to be piezoelectric, and the polymer or the matrix is to be made of polymer. This one is not new. When I started this one, I don't really see any any innovation when it comes to just using the polymer as a matrix, and we have the piezoelectric as a fiber. But then it wasn't really that so-called old. It's basically a new material that being studied. But in my case, I tried to introduce some um, uh, pores or porosity in the matrix. I read one paper. I think that was yeah, that's just one paper existing then. They did a research on using the piezoelectric composites, using a fiber as using the piezoelectric material as a fiber and the polymer as a matrix. But they did add porosity, but the results was good, initial results, but it was not extensive. So I saw that as an opportunity to be able to share some new ideas, some more innovative modeling. So in this case, we're looking at soft inclusions or porosity. So my student extended the use of soft inclusions rather than just using porosity, because the problem in introducing porosity then is there's no way or very difficult way to process this one. Now this one is giving me more interest now because of the availability of the 3D printing process. So we will be able to probably print this one if, of course, they are able to print the piezoelectric fibers. So these piezoelectric composites, they have higher electrical coupling that monolithic piezoelectric materials don't have, so they can have higher mechanical coupling. When I say coupling, I'm saying that they have higher efficiencies, meaning that we are able to harvest more, or if it's going to act as a sensor, then it's going to be more effective as a sensor. So this one will have lower acoustic impedance, so pretty much for sonars or submarines, the use of piezoelectric composites will be more suitable for them. For ceramics, ceramics on its own is very brittle. So when it comes to the use or tailoring it for curved surfaces, that can be challenging. So basically, these composites provides ways to make it flexible, and then of course we can always tailor this one. Now, what are the examples or applications of piezoelectric composites in biomedical applications? So we have biomedical imaging. There's quite a lot of research here. So basically, I stopped doing, or no, I paused a bit on doing research on piezoelectric composites because of my admin work. So you're basically looking at some applications here. I know there should be a lot of work already out there. They have been published. I did quite a brief review a few months ago, and I was able to see that there's a lot of ongoing research on the use of piezoelectric composites. So pretty much they're used for ultrasound therapy as well as tissue engineering. This one is because of healing. So there's that concept of using this ultrasonic sound or ultrasonics to be able to heal broken bones or even injuries. And one of the other one, if you cannot really go into developing some substitute for bones, is to have wearable electronics. We see a lot of wearable electronics using piezoelectric materials now. And this one is the promise of healing. So there was this study already back in 2012 that you can use this ultrasound coming from a piezoelectric to be able to heal injuries. So from bone growth to physiotherapy. This was my study back then in 2016. We tried to investigate the different applications of piezoelectric composites for a human body. So we were able to match them. Please take note that bones are basically piezoelectric. So back in 1960s, there was this published literature in Nature. Nature is basically the top journal on science. So there was this study in Nature that they were able to prove that bones, basically our bones, are piezoelectric materials. It's smart. So that's why it can heal itself. So we have identified a lot of potential piezoelectric composites that can be used for healing. And then when it comes to the market, so basically this was not updated, but as you can see, for the biomedical ultrasound imaging, this one, the market is 8.1 billion, predicted back for 2016. They can be used for novel ultrasound transducers or arrays for biomedical imaging. So this was a study in the US. And for bone healing market, so as you can see, we have this $17 billion that are spent on treating just basically Americans afflicted with osteoporosis. So basically this one is, if we look at the global market, then probably this one will be larger. We have wearable electronics. So we see a lot of wearable electronics now. So one of the challenges of wearable electronics is they must be flexible. And then of course we have this pacemaker. So there was this study on the use of a piezoelectric or implanted flexible piezoelectric nano generators for pacemakers. So basically once the heart is beating, so there is that force that's going to act on the piezoelectric material, which gives away energy or electricity. That's again going to power the pacemaker. So pretty much it's self-sustaining. When it comes to the range or the size of the material, so from ultrasound imaging, the piezoelectric materials can be micro, and then towards wearable electronics and biomedical nanogenerators, they can be on a nanoscale. So this will be the scale of the piezoelectric fibers that we're looking at. And this one was the model that I presented back then. I was ambitious back then to submit into a very high impact factor journal. I was confident because I know that I just only saw one paper then, and I don't really see that there were any publications. So I was very ambitious to submit my study on a very high impact factor journal. It's called Acta Materialia. The comments there were not really technical. It's basically my grammar and my writing of the journal paper. So these were the comments. Other than that, it was easily accepted because the idea then was new. And pretty much what I did here was to introduce in the model the porosity to be able to improve the performance of the piezoelectric composites. When I say performance, it's pretty much the efficiency. So this is the model that I presented. This model was basically presented by a Japanese researcher. So they call it the Mori Tanaka method. So this Mori Tanaka method, where I homogenize a matrix by adding porosity, and then I homogenize that homogenized matrix with the piezoelectric inclusions to make it a porous piezoelectric material or composites. So this is just a simple mathematics. The mathematics is simple, but I believe that the results that I presented is very new, so that was easily accepted. So I'm just showing here the different mathematics that I used, the Mori Tanaka model. So what I'm saying here, just to show these results, so this one here below, where we have this dotted lines here, this is the performance of piezoelectric composites without porosity. So if I add porosity, you can see that the performance or the efficiency will be higher, or the output will be higher than that composite without a porosity. So this was back in 2008 Acta Materialia. The impact factor now is about 7. And so here we were able to see that this one is with 0 porosity, the one below, and the one here will be with 30% porosity. So then again, we see a very, we see that the performance really improve a lot, and with the addition of the porosity. And this one is another research of mine. This one is making smart materials, making a structural materials smarter due to addition of the piezoelectric materials. So as you can see, I have the small ones here. This one is basically a new research compared to the other one that I presented. So I put in some piezoelectric materials in a beam and see whether it's going to be smart. I was able to publish this one in Smart Structures, Smart Materials and Structures, and International Journal of Solids and Structures. So basically, I didn't receive much comment here. I think the comment here was that they want the presentation of the equations to be a lot simpler. So this was the derivation that I did for the problem that I've shown. So I'm using index notation or initial notation. This was the equation I derived to determine the natural frequency of that smart structure. This I have to derive this one, and I'm currently stuck with this one. I wasn't able to continue. It's quite difficult for me now to see how this is going to be extended, but I'm really hoping to find ways to be able to extend this one and do more research. So this one I have to derive this equation. So that will be the strain energy and the dielectric energy, two energies that's contributing to the natural frequency of the smart structure. So this was just a simple, just showing the full equation that I was able to derive for this project alone. And I was successful in publishing this one. So I have 2 journals based on my study on this one alone. And I hope to still continue this one later on if I have time to further improve the equation and predict more complicated structures. So as a summary of my piezoelectric composite research, I've published them in high impact factor journals. So you have Applied Physics Letters. The mathematics is very simple. There's a lot of comments from my peers that they're saying that it's very simple, but the idea then was very new, and that was in 2013. The idea was very new, so I didn't really receive any comments here. Actually, in Applied Physics Letters, what really happened here was that there was this reviewer, a Russian reviewer. He showed me his he showed me a journal in Russian that this was done sometime in 2000, but it was a paper written in Russian. So there's no way that we can access this one in an English journal. So he presented me, or he showed me that there was that study already, but it was not really popular then because, of course, it was in Russian. So there you go. I was able to publish this one, 2013. This one is the other. When I started that research of mine, I had a gap here because I work in the industry after my after being a postdoc at NTU and in the University of Southampton. As you can see, well, we have sensors and actuators. We have International Journal of Solids and Structures and Smart Materials and Structures. So this research area is, I believe, very active, and they can be published in high impact factor international journals. For the composites, definitely. I'm a reviewer for many journals, international journals on composites, owing to my previous work in composite materials. So I see that there's a lot of opportunities in conducting research on the use of natural fibers, especially in the Philippines. Of course, we have a lot of resources, and I don't think the investments for research will be high. Some testing equipment, ways to be able to develop composite materials, and of course, we have to be very strong in mathematics and science, and we have to know how to use computational tools. Okay, so that's just for me. That's just from me. I really would like to thank the Polytechnic University of the Philippines. I would like to thank you all for joining this presentation. Maraming salamat po.
Thank you, Dr. Della. We are now on the open forum. If anyone has a question, kindly just type it in the chat room. Sir, the question is first, um, I'm also curious about this. Is piezoelectric AC or DC? And is quartz a piezoelectric material?
Sorry, can you repeat the question, please?
Is AC is piezoelectric AC or DC? And is quartz a piezoelectric material?
It's pretty much a DC, I would say. So when it comes to AC, or DC, didn't really come out. So I would really consider that to be a DC. So I wasn't electric part of it. I'm more on the materials and modeling structural study on that part. So I would think it's DC.
Okay, sir. Is quartz a piezoelectric material? From
Quartz,
from
yes.
Fernando Bellarmino.
Piezoelectric materials, the some materials, PZT, lead zirconium titanate is basically a quartz material. So a lot of the ceramics, the ceramic piezoelectrics are basically quartz materials.
Sir, question. I've learned today that actually when we think about piezoelectric, we are thinking about producing energy. And I've learned today that it is actually better as a smart material or a sensor. So my question is piezoelectric material a practical power source or an alternative energy resource?
From a large scale point of view, no, it's pretty much just a substitute just for small applications. So some shoe companies are looking at harvesting the energy from the shoes when someone is running or walking, and they're basically using piezoelectric for that. Maybe some vibration, some small vibrations or continuous vibrations, we can harvest those to be able to power LED, because we know LED requires a small amount of energy. So these are the applications. But when it comes to a substitute, no, I don't think so.
Yes, sir. So, sir, more of its application are on highly efficient technologies that utilizes a small amount of energy. But when it comes to research, it is better for us to consider that as a sensor and a smart material.
Can be a sensor, but there's a lot of research already ongoing on trying to be able to harvest that. So you can use it as a sensor, an actuator at the same time, an energy harvesting device. So nobody's stopping us from including that property of piezoelectric material.
Sir, another question from Engineer Chuck A. Ramon. How do you see this technology in the future of the Philippines?
Well, at the moment, I see this one still as a research. Of course, for more well-developed countries, they probably can look at this one as already developing a product. But in the Philippines, it's probably more on a research basis, especially for those in the academia that they want to publish in international journal papers. These are basically the areas that you would be looking into. I've heard a lot of research proposing to me or just discussing with me. They say research they want to publish in international journal papers, and pretty much is just putting one component on top of the other. And that doesn't warrant any publication. So I think in terms of research, especially for those in the academia, these probably are the areas that you would like to look into. The type of areas, yeah.
Sir Armando Corpus of PSU is curious if the piezoelectric composites can resist fire, or can we design it to resist fire?
Probably you can add more materials so that the outer covering will be able to resist fire. Maybe add a bit more ceramic covering, and try to see to it that there won't be too much heat coming into or entering into that piezoelectric material, so that it won't affect its operation or performance.
Sir, regarding the porosity, you showed a while ago that in the image you showed, it's the 30% porosity, meaning you put 30% on the material level of
Matrix,
porosity.
yes.
That's the most efficient. Is that the most efficient, or is that the limit of introducing porosity to the material, 30%? Or you
Not
could
really,
do
because
50%?
I've tried higher 40%, but the thing is, you have to consider that you also have a fiber, and the
Yes,
matrix should be holding that fiber.
yes, sir.
So that's the that was my initial consideration then. So I cannot have more than 30% because the matrix is the one that glues the fibers.
Yes, sir. I'm just curious, what percentage of porous would make the material um not efficient anymore, or yung mag magiging fragile na siya, or it
Yeah.
would be more
I
efficient?
haven't tried that. In theory, you can have anything in theory. So I just have to limit from the point of view of application, because there was this when I also presented this paper in a conference. So I have a different research. So I showed it to the conference to be able to get more feedback. So this was the comment really. Yes, I agree. That was a common comment. What will be the maximum? But the thing is, the discussion there was you have to see to it from the point of view that your matrix is also a binder.
Sir, Miss Megan Kim Dongka is curious if there is limitations to the generated voltage of uh piezoelectric material.
Yeah, there can be limitations, of course, based on its size, of course, depending on how much you use it. For your application, there will be a required dimension. So the dimension is going to limit the output of that piezoelectric, the energy that's going to be outputted by that piezoelectric material.
Sir, Sir Fernando Lipardo is curious and on the cost of composite piezoelectric materials.
Uh,
And is it being produced nowadays?
yeah, it's being produced. The piezoelectric materials, they're quite cheap, actually, for some of the common piezoelectric materials. The one we use in our cell phones, that's why it vibrates. So yeah, what you do there is to once it rings, so you have to what do you call this one? You have to input an energy there so that you achieve a resonance. So it's going to vibrate a lot. So that will be for our cell phones. And some sensors basically just cost $1 for a small sensor. Of course, a more expensive ones that we use in the wind industry for our research can cost about $6,000. But it can be varied. So for small research, it probably won't cost you a lot, just for research purpose. But in my case, for research purposes, we can always start with some mathematical modeling, some simulations, and yeah. After that, then you can proceed to spending a few money to be able to test it.
Okay, thank you, sir. I think that would be all. And thank you, because at the end of the day, I really learned a lot about piezoelectric materials today, because our students are actually trying to utilize piezoelectric material in their research as a source of power source, a source of alternative energy. But at the end of the day, their results is actually not practical to be used in as an alternative power source. And it's a good thing that we now have an idea that it could be really a smart material that we could utilize in biomedical and in robotics and in other sensor purposes that could be our uh, line of research nowadays. So as we could create better research and better research paper. Thank you, sir. To give to award the certificate of recognition, may I call on the Dean of the College of Engineering, Dr. Remedios G. Ado.
Polytechnic University of the Philippines, this certificate of recognition is given to Dr. Christian N. Della in grateful acknowledgement of his distinguished and invaluable service rendered as guest of honor and speaker in the Science, Engineering, and Technology Professorial Chair Lecture Series with the title Piezoelectric Composite. Given this 20th day of November 2020 at the PUP Main Campus, Santa Mesa, Manila, Philippines. Signed, Dr. Manuel M. Muhi, University President.
Thank you very much, ma'am.
Polytechnic.
To our participants, thank you, Dr. Delia.
Thank you, everybody.
For the evaluation of our seminar for today, kindly look at this link. Where's the link? Okay, for your certificate, kindly, for the evaluation form will be available only from this point on until 11:59 p.m. today. Kindly do the evaluation at this given link. So later in this afternoon, we will also have a Professorial Chairholder lecture by Dr. Ryan S. Evangelista. Dr. Evangelista will talk about IT project management in the globalized society. So at this moment, let's have a photo opportunity. Kindly wait for a few seconds so as everybody could be included in the picture. While doing so, we would like to thank our participants from different institutions today. They are from FEU Tech, National University, IRIS, Pangasinan State University, Bicol University, DPWH Regional Office 6, PUP Lopez Branch, TIP Manila, Visayas State University, Mapua University, Makati Development Corporation, University of Santo Tomas, Pamantasan ng Lungsod ng Maynila, Catanduanes State University, University of Technology, Isabela State University, Cavite State University, De La Salle University, Philippine Society of Mechanical Engineer Davao, Nueva Ecija University of Science and Technology, Quezon City University, Future University of Sudan, Asia Pacific College, Fiati University, Mindanao State University, Manuel S. Enverga University Foundation, Holy Cross College, Malayan Colleges of Laguna, students from PP, SHS and Mabini Campus, PIES NIA Chapter, Biliran Province State University, and our President Manuel M. Muhi. We hope that we could see you as well this afternoon for the 2 p.m. lecture.
University of Rizal System Cainta is also with us.
And University of Rizal System Cainta.
Kindly open your video.
Okay, that would be all. It's photo off pa po. May nag-take pa rin po sila ng picture.
First slide po tayo. Paki-open na po yung camera. Okay po. 1, 2, 3. Na. Okay. Wait lang po. Okay. Next po tayo. Next slide po. Okay po. 1. Pa-open po nung sa next slide po. 1, 2, 3. Okay. Next slide po. 1, 2, 3. Okay. Slide po. Okay. 1, 2, 3.
Last slide.
Slide po. 1, 3. Okay. Slide po. Ano pala yung last na po? Okay po. 1, 2, 3. Okay po. Thank you po.
Okay, thank you. The correction, the talk of Dr. Evangelista this afternoon at 2 p.m. will be about Introduction to Cloud, the future of modern computing. We will be back at 2 p.m. Thank you, Dr. Della.
Thank you very much to all.
Thank you, sir.
Yung pinupost natin sa future events. Sabi. Apo, pa rin ang